Afternoon, everybody awake still? Okay, so we've talked about building software. We've talked about distributing it out across lots of computers, maintaining the state in multiple places, having great introspection so we know what's going on. Everything's solved, right? Everybody's had a computer fail at some point, right? We all know that eventually the shit hits the fan, right? A storm happens. I was at a data center one time where we had a pipe leaking onto servers from the top down. So we've got to be able to deal with wide-scale disaster failures that take out large swaths of computers, even when we've got them widely distributed. So we're going to bring up Justin and Shruti, and they'll be talking about Facebook's approach to mitigating that sort of data center scale outage. Guys?
Hello, everyone. I'm Justin, and this is Shruti. And in addition to being the only thing besides Yijin standing between you and drinks, we're going to be talking about how Facebook mitigates data center disasters. Now, these types of disasters can actually take many forms, such as hurricanes. Take Hurricane Sandy in 2012. For Facebook, Hurricane Sandy was a wake-up call. Sandy came within 30 miles of our leased data center and narrowly avoided our Forest City data center.
If Sandy had hit either one of these, Facebook would have gone down. Why? Because at that point, all of our primary database shards were placed in Forest City. This is especially concerning to us because people have come to rely on Facebook and our other services to coordinate response efforts during disasters and to make sure friends and family are safe. Fortunately, Sandy avoided us narrowly, but we asked ourselves the question, can we run Facebook without one of our data centers?
So what we're going to do today is talk about how Facebook deals with disasters, both that take down data centers offline, like hurricanes, as well as disasters that take just portions of data centers offline, like snakes crawling into power transformers and shorting them out. And that's a real example, by the way. For each of these, we're going to share the problem, our solution, and interject in between how the theme of immense scale that's hopefully relevant to all of you in the audience is influencing our approach and leading us toward new challenges in the field. So let's go back to the question that got us thinking about disasters. Can we run Facebook without one of our data centers? To understand why this question is challenging to answer, let's take a look at what goes on when I take out my phone and access Facebook. Well, a request is sent to a web server in one of Facebook's data centers around the world. And that web server communicates with many microservices to fetch posts, comments, reactions, ads, and so on. What would we like to happen when a disaster occurs? Well, when a hurricane is heading toward one of our data centers, we'd like to be able to redirect traffic away from the data center toward other healthy data centers. At Facebook, we call this operation draining the data center. And we'd like to be able to drain data centers with zero user impact. This should be easy, right? We should just load balance all of the traffic away from the data center.
But, like everything else, this is far more easier said than done. This is especially problematic at Facebook's scale because while Justin walked you through an example of the journey of a single web server request, what he didn't tell you is that at Facebook, we actually run thousands of these microservices. This zoo, as Ben put it in the morning, of microservices, each have their own requirements, own constraints, and might have dependencies on other microservices. Spread these thousands of microservices in potentially unpredictable manner across tens of data centers across the whole globe, and you begin to see the scale of the problem that we needed to solve.
And as Shruti alluded to, at Facebook, we don't run cookie-cutter data centers that all have copies of the social graph with every service deployed in each of them. And while that would make our lives easier, it would lead to underutilization in our data centers. In addition, dependencies between all of the microservices lead to far more complex operations when we do need to drain safely. For example, we can't just start draining cache servers, because web servers that use the cache as a buffer to accessing database servers would start sending a thundering herd of requests to the databases, overwhelming them. So for correct and safe drains, we need to drain systems gracefully, based on their dependencies. And at Facebook's scale, it's actually much more complex than that. This is Facebook's major service dependency graph. It's a bit different than some of the call graphs that we saw in the analytics talks earlier in the day, specifically because here, what we're looking at are the order in which we need to drain services to safely drain an entire data center. So how do we actually use this to drain data centers safely and efficiently? Well, we relied on a couple of reliability fundamentals. For example, capacity provisioning is what makes sure that services are sized correctly to handle the additional load that's put on them when we drain entire data centers. And global replication is what lets us assure that we have data available in the data centers to serve requests even when one of them is drained. And while a naive solution to this problem would just be to over-provision our services, we instead worked carefully with capacity planning teams to make sure that services had the minimum amount of capacity necessary to survive data center failures. And while this took time to get right, once we had a stable foundation to build upon, we could actually start to think, what are the types of tools and abstractions that we want to provide to drain data centers safely at Facebook's scale? So this was actually the very first version of how we drained data centers. It was as simple as a whiteboard with steps written on it. And at Facebook, we call the steps used to perform a production operation a runbook. It might not look like much, but starting simple and iterating quickly actually helped us prototype the operations and understand dependencies between services efficiently. But as our data center fleet grew from 3 regions to 5 regions, we quickly found out that this whiteboard space just wasn't enough. And so for our next iteration of draining data centers, we used war rooms and spreadsheets to coordinate the work of engineering teams. Now, you can probably imagine sitting in a war room for 8 hours without much of a break. It can be tiring, and you might feel stressed if production operations arise that actually lead to incidents. So, keeping this in mind, we wanted to design a tool that could actually assist us when draining data centers. So we started working on a system to automate the steps needed to drain a Facebook data center and track their performance. This work allowed us to dramatically improve drain speed and decrease errors. So let's fast forward to today. Here's what our system looks like for draining data centers in action during a recent large-scale production test. This is the front-end UI that is exposed to site operators, and each of the rows represents a task that needs to be performed. A back-end scheduler takes tasks and transitions them to a runnable state, shown in purple, when all of their dependencies are satisfied. Then, automation kicks in to start running the steps, and they're shown in blue here. Finally, we have validation that's attached to each of the steps in the runbook, and this allows us to verify when an operation has actually completed. Now, what's happening behind the scenes is we're using the same dependence graph that I showed you before, overlaid on top of these production operations, enabling us to ensure that we can do all of this safely. Now, at Facebook's scale, the infrastructure and software landscape is constantly in flux. And it's possible that unintended dependencies creep up, or services just see unplanned growth and invalidate some of our design time assumptions. To prevent against this, we do quarterly tests at scale to verify that we can gracefully lose any Facebook data center. These tests are run without any advance notice. They take a couple of hours to drain all traffic completely and ensure that dependencies are valid and our tools work. An explicit goal of these tests is to have no user impact. So where are we now? Well, last year when Hurricane Florence was once again hurtling toward our Forest City data center, we used our tools to redirect production traffic away from Forest City to other data centers. The process was highly automated, as I described, and traffic from our front-end apps was redirected in minutes, with stateful services being the ones that actually take the longer amount of time to drain, but still within 2 hours, resulting in no user impact whatsoever. And although this has allowed our engineers to sleep more soundly at night with regards to large-scale infrastructure failures, this technique still has its limitations. For example, since this relies on shifting traffic away from a healthy data center, from the unhealthy data center to other healthy data centers, we're not able to handle widespread outages that could happen due to, say, server misconfiguration or bugs.
But for the purpose of this talk, let's stick to the scope of non-human-made infrastructure failures. So we've seen hurricanes, but what else can go wrong? Apparently quite a lot. We've seen the whole gamut of elements of nature strike us, like that snake that crawled into one of our power transformers and shorted a main switchboard. Luckily, we were able to employ one of the runbooks that Justin talked about and drain all traffic outside of that data center while that switchboard was being repaired. And Facebook was saved. Fortunately, not the same for that poor snake. We've also seen lightning strikes on our switchboards. We've seen hardware catching on fire. We've seen water leak short our motherboards, and so on. We've noticed that within our infrastructure, we see a lot more of such kind of failures, those that are well contained and are on a smaller scale than an entire data center. And unlike hurricanes, these don't come with a warning, but they have a much smaller blast radius. Upon studying previous infrastructure failures like these, we noticed that a majority of them happen along the power path within a data center. So let me walk you through how power is distributed within a data center. A data center building is typically split into suites. A suite is powered by a few PDUs or a power distribution unit, which distributes power to smaller PDUs and so on until power reaches the rack and individual server machines. So now a lightning striking a PDU is similar to a campfire-sized failure in a forest. Now, one way of extinguishing this fire is to employ the strategy that Justin spoke about and drain all traffic outside of this data center. But this solution would be akin to bringing in a helicopter to douse an entire forest with water where clearly a bucket could have sufficed. So this is not only wasteful and inefficient, but it also comes at a big cost and is an inconvenience to all the other campers in the forest. So since the risk posed by such failures is different, we should also treat them differently or deal with them differently. Based on previous infrastructure failures, we identified one physical domain that encompasses a majority of these failures, which I will henceforth refer to as a fault domain. Some projection studies that we did show that the frequency of such failures or sub-data center failures is going to increase quite rapidly as our infrastructure scales. Draining a full data center then would mean bringing in a lot of helicopters to douse a lot of forests with water unnecessarily. This is not only wasteful, but it also poses a higher risk, a higher stress to all of the other forests infrastructure. So what about partially draining a data center then? Server generations across fault domains across our fleet vary quite diversely, especially as new capacity is being added and old capacity is being decommissioned. This hardware heterogeneity across the data center means that a lot of our software is spread non-uniformly across them. So creating and maintaining dependency graphs and runbooks, like Justin mentioned, for each of these fault domains is a bit intractable. And in any case, with a lot of these kind of failures, we see that a graceful drain is not even viable. So we decided that we needed a different strategy to deal with such kind of failures, one that expects the service to be able to gracefully handle the unexpected loss of a fault domain.
But before Shruti goes in and discusses the approach, I just want to jump in really quickly and emphasize the scale of the sub-data center disaster recovery problem. Imagine having to test all of those fault domains that Shruti pointed out across the entire infrastructure without the help of runbooks, just pulling the plug, so to speak. And imagine now that the rate of occurrence of those types of issues is projected to increase by almost an order of magnitude over the next few years. At Facebook's scale, we had to make sure we had a solid approach to these types of disasters.
So the approach we took adds on to the fundamentals that Justin talked about with the whole data center failure problem, which is capacity provisioning and replication. So one thing is that we need to provision services with enough capacity, enough but minimal capacity to swallow a loss of a fault domain. But just having enough capacity isn't enough. We need to be intentional where to physically place this capacity. And by capacity, I mean it could be servers, both storage and compute. It could be network infrastructure. It could be cooling infrastructure, et cetera. The more evenly hardware is spread across the data center, the less impactful it is to lose any one single fault domain. But again, balanced hardware spread doesn't itself guarantee balanced software spread. So services also need to be intentional about where their software is being placed within a data center such that they can tolerate the loss of a single fault domain. And third, the service should be able to fail over correctly and automatically in case of failures. Ensuring that these three conditions are met, especially when we're dealing with all of those thousands of different kinds of microservices, and they could be of different sizes, they could have different deployment scopes, they could be dealing with different kinds of traffic. This can get a bit challenging. Let's dig into this a bit deeper by broadly categorizing our services into categories of stateful and stateless. A majority of our stateless services are managed by the Tupperware platform that Kenny just described. So to minimize operational overhead from the service owner's perspective, the Tupperware scheduler is expected to distribute a service's jobs evenly across all fault domains, such that no single fault domain is a single point of failure to a service. And upon failure, the Tupperware scheduler is expected to preempt and migrate all of the affected jobs onto healthier pastures. Achieving this kind of fault domain tolerance is a bit harder when we talk about stateful services, because this involves data placement in a way such that failures can be tolerated without data loss or data inconsistencies. So stateful services, it could be Zookeeper, it could be the DLoS system that we talked about earlier. They need to be deliberate about how they manage data replication, how they manage data sharding, and data placement in a way such that upon failure, data can be recovered or reconstructed in a time-bounded manner onto healthier capacity. So these are some of the default methods that I described that we use at Facebook. But there could be services that lie somewhere along the spectrum here. Or there could be services that don't necessarily fit onto these standardized platforms. So even with software placement, there seems to be no, or there is no one-size-fits-all kind of solution that applies across the entire zoo. Add to this requirements that some services could need special hardware types, that those hardware need to be spread in a specific manner across the data center. Add to this the challenge that we could lose multiple fault domains across multiple data centers simultaneously. And all of these lead to challenges that becomes a little bit hairy to solve as a site reliability engineer. So we developed a constraint specification language that services can use to define their availability and capacity constraints or requirements. These constraints can look like, for example, how many hosts I can lose before my service will become unhealthy, or how many replicas within my replica set need to be alive to achieve right quorum. These constraints are continuously used to audit the entire fleet, and this gives a good visibility into the entire fleet's health, such that a site reliability engineer can always pinpoint which service is at risk in which data center region. These constraints, if a constraint is violated, the capacity is automatically reprovisioned, software is rebalanced such that the site's health is maintained. These constraints are also used during new capacity turn-up time and capacity decommission time, such that a service's risk to fault domain failure is always limited and known. But just as Justin mentioned earlier, similar to runbooks, these constraints can also go stale. And so we need to continuously validate them. And similar to the hurricane risk mitigation tests, we also run fault domain tests in prod with the same success criteria, that is 0 user-facing impact. We run 2 kinds of tests. One are soft tests, where we isolate network on hosts within a fault domain, and we also run hard tests, where we partner with data center operators to literally pull the plug. Continuous testing at a high cadence in order to achieve high coverage across all of the fault domains is a high priority for us. So to tackle disasters at Facebook, we've had to think about data center fault tolerance in a structured manner in the face of rapid growth. One that evaluates risks posed by various kinds of failures and provides expectations to services for best practices for reliability. If any of you have ever had to work on data center level reliability, you've inevitably had to run into one of these. And this is the path we took at Facebook, and we would love to discuss the approaches that you've taken at your company as well. To summarize our talk today.
So if there's 3 things that you take away from this talk, we hope that they're these. First, as I started out by talking about, there's disasters like hurricanes that pose a risk to infrastructure when you're operating at scale. And we saw how tracking dependencies ensured that we could provide the people who use Facebook a seamless experience, even as we're draining entire data centers. Second, as Shruti talked about, for sub-region failures, we adopted a constraints-based approach that allowed us to instantaneously put out campfire-sized disasters without bringing, with a bucket of water, without bringing in a whole helicopter and draining the entire region.
And throughout it all, we discussed how the immense infrastructure scale of Facebook poses new challenges, and hence we need to continuously verify to make sure that our tools are greased and bug-free, or as bug-free as we can, and that all of our assumptions are valid. So over the course of this really long but really interesting day, we've seen how a lot of you are building a lot of really cool distributed systems and are making it, and are proposing really cool solutions to make it scale. As infrastructure engineers, we need to be able to support that, and in order to do so, we're super excited about all of the future challenges that we're working on, or we want to start working on.
And as we say at Facebook, this journey is 1% complete. And our infrastructure is only going to continue to grow. So what are some of the problems that we've started to explore solutions for? Well, we expect to see more heterogeneity both in the hardware that our services run on and the service landscape itself, which can introduce new failure modes, such as in the network domain. Everything ranging from router failures that might take minutes to hours to fix, all the way up to transoceanic links going down, requiring weeks for repair while a robotic submarine goes down to actually patch it up. And with Facebook's rapid software development cycle, within a given day, the infrastructure can change in so many different ways, from hundreds of services being pushed to new capacity being provisioned, old capacity being decommissioned, and other outages that just naturally happen in the background. To keep up with the scale of our growing infrastructure, we envision having more uniform languages for expressing dependencies and their constraints. And finally, as the number of fault domains within our infrastructure grows, the chance of experiencing concurrent failures across different data centers also increases. Validating that our infrastructure is resilient to multiple independent outages adds another layer of complexity to the problems that we talked about today. And we want to be able to do this while maintaining high correctness and high coverage in our tests. Now, the good news is, while these challenges are massive in scale, having access to Facebook's infrastructure all the way from the lowest level of server design up through the highest level of systems building and operation is what provides us with a really awesome opportunity to go out and solve these challenges.
So thank you for listening to us, and we'll take your questions now.
Yeah.